Yes. Hey, welcome back. Now let us solve the problem LCA in a binary tree. So what does LCA mean? So imagine you're given a binary tree. Okay, all these trees are small. So let's just write our own binary tree. 4, 5, 6, 7, 8, 9. Yeah, let's just format it once. Yeah, let's better than this. Let's use the tree visualizer. We need a binary tree visualizer. Yeah, I have already had some tree over here. And let's just take this tree as an example. So you're imagine you're given the nodes 11 and 13, and you're asked to find its the least common ancestor. The least common ancestor means nothing but the parent which is common to both the nodes. So if you consider 12 and 13, the parent which is common to it is 0, and no other nodes are common. But if you consider 12 and 11, the parent which is common to it is 8. And if you consider 7 and 12, the node which is common to both of them is 4. And if you consider 7 and 4, the node which is common to both of them is actually 4. So the least common ancestor will be 4. So I hope you got to know what least common ancestor means. So let me just remove this for now. And you're tasked to find that. So what can be done? So one of the approaches which seems pretty obvious is just going through each node. Like what we'll do is we'll go through the entire tree and do some mappings. Like 1 is mapped to 0. 4 is mapped to 1, 3 is mapped to 1. In other words, we'll have a mapping list. And then what we'll do again is that we will create a path. For example, if we are given the node 12, so we'll create a path from 12 to 0. So 12, 8, 4, 1, 0. Because 0 is the most highest parent, grandparent, or whatever parent you can call. 12 can't have any value which is higher than 0 as its parent, grandparent, or something. This will always be the topmost value. So we'll do one path like that. And then what we'll do from again from the other node, like consider 11, we will, okay, we consider 7 or 11, both makes no difference. We will start to make another path from the current node to root. And during creation of that path, but any chance we encounter the other path which the other node did, that means that we have an intersection. In other words, that is the parent. I hope you understood. So first we'll do a line from 12 to 0, and then we'll do a line from 7 to 0. And the point where the lines of 12 and 7 intersect is the point where the highest common ancestor lives. So okay, let's consider the example of 12 and 13, and let's just check it out. So we'll do a line from 12 to 0, and we'll do a line from 13 to 0. And you see that 0 is the only point where both of them intersect. So that will become the least common ancestor. Yeah, as soon as we get to know that basic thing, so we can directly do that. So first of them, we'll do the mappings. And yeah, since we have a root over it, so mappings for root will be mapped to -1 because as you see, root cannot have any greater parent. So root will always be -1. And yeah, since I prefer level order traversal, we'll do a level order traversal to do the mapping. So let's just write out the entire thing for doing a level order traversal. And what you have to do. So while q exists, I don't think you have to do like this. Yes, you can just do what equals. And if no dot right exists, then we'll do q dot append no dot right. But now we have to do the mapping. So how was the mapping to be done? One is mapped to 0. In other words, child node is mapped to parent node. Let's consider some other things also. So 12 will be mapped to 8. So what we have to do? We have to take the node 12, which is the child of 8, and map it to 8. And let us consider another value. So let's consider 6 and 2. 6 will be mapped to 2. So what we have to do again? We have to take a child node, which is the right node, right or the left node, regarding of whichever it is, and we have to map it to the parent node. So what we will do? If the node dot left exists, and since it is given that all the values are unique, that is the only reason you can do this approach, or else you could not do this approach. So what we will do? node dot left dot data, you will map it to root dot data. And if the node dot right exists, so you do the same thing. Node dot right dot data. So by now you should have had all your mapping. So let's just check it out. So let me return node with value 6 for now, and let us just print the mappings, and let's have a tree which you will definitely know how it is. So let's just do it, and yeah, we'll have let's have 4 and 6 as the nodes to be circled, and 1, 2, 3, 4, 5, and 6. So how will this tree be? Let's just mm, delete, delete. Yeah, this is our actual tree now. Let me just delete. Yeah, this is how the tree should look now. So what we should see is that uh, yeah. So now what we should see is that we should see. Okay, let's make it 0, 1, 2, 3 only. 0, 1, 2, 3, 4, 5. Yeah, this is the actual tree. And so what we should see is that we should get the value of 1 to 0, 3 to 1, 4 to 1, 5 to 2, 6 to 2. Okay, you can't do like this. You have to take length of q only, because the actual q is also getting mutated by adding or subtracting. But when you do length of q, it does not come, because the value of the length of q will always be constant until unless we check for it again. But the actual q will always be modifying, like always be getting modified by adding the values of left and right. And I forgot, and I made mistake in typing print. Yeah, I and yeah. Now let us see. Okay, again I made a mistake over here. So you should not do root. You should do root dot data. Now let's compile and run. And yeah, 0 is mapped to -1. Let it be. And as you see, 1 is mapped to 0. 2 is mapped to 0 as expected. 3 is mapped to 0. 4 is mapped to 0. So I made a mistake somewhere over here. It should never be root dot data. It should be node dot data. You should be able to spot when you made a mistake like that. Like as soon as I saw it is 0, I went and saw what was 0 and it was my root. So I go to know I made a mistake over there. Yeah. So 1 is mapped to 0, 2 is mapped to 0, 3 is mapped to 1, 4 is mapped to 1, 5 is mapped to 2, and 6 is mapped to 2. Yeah, that is exactly what we needed. So now we have the mappings. So first let's draw the path. So path is like this, and first it will have the root, which will have the value of n1, and while n1 actually exists in our mappings. So consider we are checking 3. So while 3 is there in our mapping, so what we have to do? N1 is equal to mapping at the position N1. So what will happen is that after first iteration, what will happen is that the value of N1 will become 1. So let me just yeah. After modifying, let's append it to the path, and let's just print the path. Yeah, I think I have put 4 and 6. So yeah, 4 goes to 1, 1 goes to 0, and 0 goes to -1, which is as expected. See, 4 goes to 1, and again 1 is there in a mapping. So mapping at the position 1 is actually 0. So 1 goes to 0, and 0 is mapped to -1. So after that, it goes to -1 and gets terminated. That is what is expected. So rather than having mappings over here, because we have to check if it exists, path over here, so we will have a visitor set. And so since we don't want to add the last final value, like -1 should not be added. So even before checking, appending it to our path, like what you call, so even before checking the value, if it is minus or not, we will add it to visitor. So this will assure you that -1 will never be added, but every value from the node to the root will be added. N1. And mapping set the position N1 is equal to N1. Yeah, let's just print visited now and verify it. So again, visited should contain 401. Yeah, it contains 014 or 401, whatever you want to call it. And now what we have to do, we have to draw a second path from our second node to the root node. So we'll do the same thing. While N2 also exists in our mappings, when we started to draw the path, but at any instant of time, if N2 exists in your visited, that means that there is an intersection. So consider 3 and 4. The instant 4 1 0 is added, but the instant when you add 3 and then the instant you check for 1, when you draw line from 3 to 0, as soon as you reach 1, you see the intersection. In other words, as soon as you find 1, you find the intersection, and as soon as you find the intersection, you have to return the node with the value n2. Yeah. Or else what you have to do? N2 is equal to n2. And yeah, this can be kept over here because it is given that you will always have two nodes which are present. And yeah, 0 expected 0 because we had 4 and 6, the expected is 0. Let's just change it to be 4 and 3 and check it out. Now the expected should be 1. The answer should be 1. And as you see, expected and answer match. The only difference is I'm printing out the mappings over here. So let me just remove this. And yeah, let's just submit it and check once. And yeah, as you see, the code works and that was what was expected. So again, let me tell what is to be done. So you're drawing a line from your given node to the root node, like first node, and then you're drawing another line from your given second node to the root node. And at any point of time, if the line intersect, that is your parent. Yeah, the algorithm is as simple as that, and that is what we have successfully done over here. And yeah, that's all for it. And thank you for watching, and goodbye.